Black holes are real. They exist and we observe them all the time. Not only do they exist, but they also shape the universe that we live in. Have you ever wondered if we are really alone in the universe, or if there's more to our existence than meets the eye? What if the James Webb Telescope finally proves that we live inside a black hole? Join us as we explore this mind-bending, earth-shattering news that will leave you questioning everything you thought you knew about the universe. So, what are black holes to begin with? They're the stuff of nightmares. Sure, you may have seen them in sci-fi movies, but the reality is even more terrifying. According to some scientists, black holes are just pitch-black holes in space. But the truth is a lot more complicated. Black holes are actually massive amounts of matter squeezed into an incredibly small area. Imagine a star that's 10 times more massive than the Sun, all packed into a sphere the size of New York City. The gravitational pull is so strong that nothing can escape from it. Not even light. Scientists have been fascinated by black holes for centuries, ever since they started theorizing about objects in space that were so massive and dense that they could trap light. The most famous ideas about black holes were predicted by Einstein's theory of general relativity. Basically, when a massive star dies, it leaves behind a tiny, dense core. If the core's mass is more than 3 times the mass of the Sun, the force of gravity overwhelms everything else. It's a pretty cool and mysterious phenomenon, but also kind of creepy when you think about it. So how do scientists detect these black holes? These things don't emit any light, so you can't just point your telescope in their direction and snap a photo. In fact, detecting black holes is a real challenge, but scientists have found a way to infer their presence by observing their effects on nearby matter. It's all about watching for the signs. For instance, if a black hole passes through a cloud of interstellar matter, it will pull that matter toward it in a process known as accretion. But that's just the beginning. If a normal star strays too close to a black hole, it's game over. The black hole can tear that star apart as it pulls it toward itself, and as the attracted matter accelerates and heats up, it emits X-rays that radiate into space. That's how scientists are able to detect the presence of black holes indirectly. But the real kicker is this: black holes have a dramatic influence on their surroundings. They can consume nearby stars, emit powerful gamma-ray bursts, and even spur the growth of new stars in some areas or stall it in others. It's a mysterious and shocking phenomenon that's sure to give you the creeps. And where do they come from? Picture the stars, once magnificent and blazing, meeting their ultimate demise in a spectacular explosion called a supernova. From the remnants of these fallen giants, a mysterious entity emerges, the infamous black hole. Now, don't let their name fool you. These celestial enigmas aren't just ordinary holes. They're like the vacuum cleaners of the universe, devouring everything that dares to come near. Most black holes are born from massive stars that have reached their celestial retirement party in a supernova blast. It's like the grand finale of their stellar existence, leaving behind a void of eternal darkness. Smaller stars, when they kick the bucket, transform into something called neutron stars. They're super dense, but not dense enough to trap light. However, if a star is a heavyweight champ, about 3 times the mass of our humble sun, then a mind-boggling possibility arises. Theoretical gurus have proven that no force in the universe can prevent this star from collapsing under its own gravitational pull. Talk about a crushing destiny. As this mighty star crumbles, something strange starts happening. The surface of the star gets closer and closer to an invisible line called the event horizon. Here's where things get really trippy. Time itself starts playing tricks. From the perspective of someone far away, time appears to slow down near the event horizon. It's like the star's own clock ticks at a different pace compared to ours until, at that fateful moment when the surface touches the event horizon, time freezes and the star can collapse no more. It's like a frozen implosion, frozen in time. Pretty spooky, right? But guess what? There's an even more haunting twist to this. Sometimes, when 2 smaller black holes meet in the cosmic mosh pit, they collide and combine, creating an even bigger and scarier black hole. And just when you thought things couldn't get any darker, imagine a black hole teaming up with a neutron star. Their deadly dance forms a colossal nightmare, a terrifying entity that defies all comprehension. Scientists have been struggling to wrap their heads around the scale of these sizes for years. It's like there's a sinister mystery surrounding them that we can't seem to unravel. The thing is, black holes come in two sizes, huge and small. But here's the catch: small is relative. Stellar mass black holes are remnants of massive stars and can be as large as 10 to 24 times the size of the Sun. There could be as many as 10 million to a billion of them in the Milky Way alone. That's an astronomical number of black holes that could swallow anything in their path. But wait, there's more. Supermassive black holes are on the other end of the spectrum and are millions, if not billions, of times larger than the Sun. They exist at the center of large galaxies, including our very own Milky Way. It's like a gaping dark void that's pulling everything toward it. Stephen Hawking, a renowned physicist, talked about black holes in his lifetime. His lectures were always insightful, but some of his theories couldn't be confirmed due to a lack of necessary equipment. However, there's hope on the horizon. A single scientific instrument is changing everything, and we are not ready for it. It goes by the name of the James Webb Space Telescope, also known as JWST, and it's here to plunge into the depths of our universe. The JWST is no ordinary telescope. It's an engineering marvel, a testament to the potential of human ambition. Sure, we've launched other space telescopes before, and they've been doing their jobs just fine, but this one is in a class of its own. The JWST makes the Hubble, which has dutifully served us for years, look like a mere speck in the cosmos. The price tag of this astronomical wonder is a whopping $10 billion. Yes, you heard that right, that's enough zeros to make your head spin. And get this, it took the combined efforts of NASA, the European Space Agency, and the Canadian Space Agency to bring this marvel to life, not to mention the invaluable input from over 300 universities. But let's not forget the risks that come with such a grand undertaking. Oh no, this isn't a venture for the faint of heart. The JWST is venturing into uncharted territory, pushing the boundaries of what we know and taking us to places we've only dreamed of. Following a successful launch, NASA recently announced that the telescope has enough fuel to last more than twice its minimum mission life expectancy of 10 years. Since its launch, the JWST has made many incredible achievements. It traveled over 1 million miles to reach its orbit around the Sun, where it will reside permanently. During its journey, the telescope successfully unfolded its massive 5-layer sun shield and giant main mirror, both of which had to be folded to fit onto the launch vehicle. Now, after NASA has fine-tuned and calibrated it, the telescope is almost ready to go into full operation. One of the most exciting things about the James Webb Space Telescope was when NASA announced that it had captured its first images of starlight. The first image taken by the telescope was of a star called HD 84406, resulting in a mosaic of 18 scattered bright dots from the star's light captured by the 18 mirror segments located on the primary mirror. NASA later released a new and improved image of HD 84406, in which 18 unfocused copies of the star were brought together in a deliberate hexagonal formation. Once the observatory successfully aligns the individual segments of the primary mirror, it will begin the image stacking process. This will bring 18 images on top of each other into one clear view. Thanks to its sophisticated technology, the JWST will help scientists investigate the early stages of the universe after the Big Bang. It will study what happened after the first stars formed, a period known as the epoch of reionization. This refers to when neutral hydrogen was reionized, or made to have an electric charge again, by radiation from these first stars. This involves looking back billions of years, which is only possible with a powerful telescope like the JWST. The telescope will also help scientists discover exoplanets, which are very difficult to spot because of the way they interact with their host stars. Its powerful sensors will be able to observe these planets in more depth, including in some cases imaging their atmospheres. Understanding the atmospheres and formation conditions for planets could help scientists better predict if certain planets are habitable or not. Apart from studying the assembly of galaxies, scientists study galaxies to see how matter is organized on a gigantic scale. This, in turn, lets us see how the universe evolved. The spiral and elliptical galaxies we see today evolved from different shapes over billions of years. One of JWST's goals is to look back at the earliest galaxies to better understand that evolution. Scientists are also trying to figure out how we got the variety of galaxies that are visible today and the current ways the galaxies form and assemble. However, most importantly, the James Webb Space Telescope will help us answer the most profound questions of all. How did galaxies like ours come into existence? What secrets do the deepest, most distant corners of space hold? And will the telescope finally unveil the truth about the possibility of living inside a black hole? Understanding these cosmic giants could reveal astonishing truths about our universe. For instance, some theorists believe that our universe might itself be within a black hole. If this theory holds true, it could reshape our understanding of the cosmos and our place within it. We might discover that our entire universe is contained within the event horizon of an enormous black hole, possibly existing within another universe. This hypothesis would significantly change how we perceive the universe and ourselves. As we embark on this new era of space exploration with the JWST, we stand on the cusp of potentially groundbreaking discoveries. It's a thrilling time for astrophysics and cosmology, and the James Webb Space Telescope is at the forefront of uncovering the mysteries of our universe. Stay tuned as we continue to explore and learn more about the universe's most enigmatic features. The James Webb Space Telescope is equipped with an array of advanced instruments designed to delve into the most intricate details of cosmic phenomena. Its suite of instruments includes the Near-Infrared Camera (NIR-CAM), the Near-Infrared Spectrograph (NIR-SPEC), the Mid-Infrared Instrument (MIRI), and the Fine Guidance Sensor / Near-Infrared Imager and Slitless Spectrograph (FGS/NIRIS). Each of these tools plays a crucial role in extending our observational reach beyond what was previously possible. NIR-CAM is responsible for capturing high-resolution images in the infrared spectrum, allowing it to peer through cosmic dust clouds that obscure visible light. This capability will enable astronomers to study the formation of stars and planetary systems within these dense regions. Additionally, NIR-CAM will help identify the earliest galaxies formed after the Big Bang, offering a glimpse into the universe's infancy. NIR-SPEC is a versatile spectrograph that can observe up to 100 objects simultaneously. This ability to analyze multiple celestial objects at once is revolutionary for studying the formation and evolution of galaxies. By dispersing light into its component colors, NIR-SPEC will provide detailed information about the composition, temperature, and velocity of the observed objects. MIRI is designed to detect mid-infrared wavelengths, which are longer than those captured by NIR-CAM. This feature makes MIRI particularly adept at observing older galaxies, distant star-forming regions, and the cooler, more distant objects in the universe. MIRI's capabilities include imaging and spectroscopic functions that are crucial for understanding the formation of the first stars and galaxies. FGS/NIRIS combines fine guidance and scientific observation capabilities. The fine guidance sensor ensures that JWST remains accurately pointed at its targets, while NIRIS is equipped to study exoplanet atmospheres through transmission spectroscopy, enhancing our knowledge of these distant worlds and their potential habitability. One of the most tantalizing prospects of JWST's mission is its potential to observe cosmic inflation. Inflation theory posits that the universe underwent an exponential expansion in its earliest moments, smoothing out irregularities and setting the stage for the formation of galaxies and large-scale structures. By studying the universe's oldest light, the cosmic microwave background, CMB, JWST may uncover signatures of this rapid expansion, offering new insights into the very origins of our universe. In addition to its observational capabilities, JWST will contribute to the study of dark matter and dark energy, two of the most enigmatic components of the universe. Dark matter, which does not emit or interact with light, can only be inferred from its gravitational effects on visible matter. Dark energy is even more mysterious, thought to be responsible for the accelerated expansion of the universe. By mapping the distribution of galaxies and their clustering patterns, JWST could provide valuable clues about these elusive phenomena. The search for extraterrestrial life is another significant objective of the JWST mission. By analyzing the atmospheres of exoplanets, particularly those located in the habitable zones of their stars, scientists hope to detect signs of life or conditions that might support it. Instruments on JWST will search for atmospheric markers such as oxygen, methane, and water vapor, which could indicate biological activity. In the broader context of black holes, JWST's observations could help resolve key questions about their formation and growth. Specifically, scientists are interested in understanding how supermassive black holes at the centers of galaxies formed and evolved over cosmic time. These black holes are thought to play a crucial role in galaxy formation and evolution, influencing the distribution of stars and the overall structure of galaxies. Hawking radiation, a theoretical prediction by Stephen Hawking, suggests that black holes can emit radiation due to quantum effects near the event horizon. This phenomenon could lead to the gradual evaporation of black holes over extremely long timescales. Observing such radiation directly remains a challenge, but JWST's advanced capabilities could potentially provide indirect evidence of these processes. Furthermore, JWST could shed light on intergalactic space and the cosmic web, the vast network of filaments and voids that connects galaxies across the universe. By studying the distribution of galaxies and the large-scale structure of the cosmos, scientists can gain a deeper understanding of how matter is organized on the largest scales and how it has evolved since the Big Bang. Another intriguing aspect of JWST's mission is its potential to explore galactic mergers and interactions. When galaxies collide and merge, their black holes can also interact, sometimes forming binary systems or even merging into a single, more massive black hole. These dynamic events can have profound effects on the galaxies involved, influencing star formation and the overall evolution of the galactic environment. Gravitational waves, ripples in spacetime caused by massive cosmic events, are another area where JWST could contribute indirectly. Although JWST does not detect gravitational waves directly, its observations of the universe can complement data from gravitational wave observatories like LIGO and Virgo. By studying the electromagnetic counterparts of gravitational wave events, such as those from merging black holes or neutron stars, JWST can help to unravel the complexities of these phenomena. In summary, the James Webb Space Telescope is poised to revolutionize our understanding of the universe in numerous ways. From unraveling the mysteries of black holes to probing the formation of galaxies and the potential for extraterrestrial life, JWST represents a significant leap forward in astronomical research. As it begins its mission, the telescope promises to unveil new cosmic secrets and expand our knowledge of the universe in ways we've only begun to imagine.